Hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In this specific discussion, we're going to look at the algebra of derivatives, and basically this is going to form a set of particular rules or theorem that we're going to consider whenever we're going to perform operations with derivatives. And in this particular case, I'm going to look at a set of two rules, which basically are going to be concerning a constant sum, perhaps a constant real number that has been used in derivatives, and perhaps the summation of two functions or their sum of their derivatives. So in this case, I'm going to consider the first case, whereby we have a function f, which is a differentiable. So I've mentioned these specific terms. So f is differentiable. F is a function that is differentiable, of course, at x, and c is a constant which is basically going to be a constant that is formed by a set of real numbers, that we can be able to give f or cf, which is the product of this. So I've mentioned about the concept of a c, which is a constant, and c is going to form a set of real numbers, whereby we're going to have for all values of a c, it's going to be a set of real numbers given as such. And I've said that if the function f is differentiable at x and c is a constant, which I've mentioned given as such, then we can have cf, which is a product of a c and that specific function, differentiable, which is also differentiable at x, and cf prime can be given in terms, or the f prime, the cf prime can be given in terms of a cf prime of x given as such. So we're going to look at this specific function, and this is the function of x. So the statement is basically in terms of a theorem, whereby if a function f is differentiable at x and c is a constant, which is a set of constant of which is a part of a real number, and then the product cf is differentiable also at x, and we can have the product cf prime over x given as cf prime given as such. So this basically implies that this is a product c times the of course the derivative, which are going to be given as such. So we can be able to, or we can prove this one by considering the case of cf as a product of a function and the constant. And of course, as we said, this is going to represent f from a general illustration of a derivative. So we're going to have this one as x plus h, given from our first representation, and then cf of x given as such. And this is going to be under the general, of course, a denominator of h given as such. So given what basically the concept of h implies. So therefore, this is going to be given in terms of a c, and then we are going to have fx plus h. This is fx plus h given as such, and then minus fx all over h. So all of this will be under the constant multiple c given as such, and this of course implies that this is the product of c and f. So all of this is going to be given as f prime of x given as such. So this basically is going to be the general representation of this specific theorem, and we're going to have this one, as we said, function as the value of h tends to 0 given as such. So this is going to give us the product of the derivative and f are given as such. So we're going to consider the second case, whereby we have two functions, whereby from this specific illustration I can just have this one given as such. So if we have two functions which are going to be given as f and g, so if the function f and g are differentiable at x, and of course we're going to have this particular part whereby I'm going to do away with this. So if you have two functions f and x which are differentiable at x, then we can give their specific sums So and f plus g is differentiable at x. So this basically implies that for the two functions which are differentiable at x, their sum is also differentiable at x. Therefore, we can give the sum over f plus g prime of x equivalent to the sum over these two specific derivatives, f prime of x plus g prime of x, given as such. So as well, we can show this one to be true, whereby we're going to consider this case is going to be enough. So whereby we're going to consider the f plus g x plus h, and then this is going to be given as a minus f plus g x whole over h. So this is a general representation for these two specific functions, and this can be given in terms of 1 over h, and then that's square brackets. We're going to have the function over f x plus h, and then plus g into x plus h. So this is the sum of the two small variations for x and the g, which are the two functions. And then we are going to have this one minus, and then we're going to have minus a second set over this one without this small consideration for h, which we had mentioned, which basically is going to be given in terms of x, fx, and then of course, so this is going to be given as a a summation over these particular two sets of functions, whereby we're going to have this one minus that one. Of course, this is going to form a set of that specific derivative which we have said. Now, if you try to consider the first part, which is fxh, we can be able, or we can rearrange this particular expression to appear in a form of we give it this specific. So we can rearrange that specific expression to give us a form of x plus h, and then minus fx all over h, and then this is going to be plus g x plus h minus gx all over h given as such. So if we try to look at this, if we try to rearrange this specific part of the expression, it's going to give us this one. But from a general discussion, we can see that this basically is the f prime of x and g prime of x. And this, of course, is the summation of the two derivatives given as such. So therefore, we can prove that basically if we have two functions, f and x, which are differentiable at x, and the sum is also going to be differentiable in this specific, of course, set of x, whereby we are going to represent their derivatives as a sum of these two specific functions. So that is it for now. I hope as we come across various rules which are going to consider these two theorems that I've mentioned, we are going to apply them appropriately. So that is it for now, guys. By God bless you. Catch us in our next video.